Good morning, everybody. Oh, it's morning for me. I don't know what time it is for you, but it's morning for me. How's everybody doing? We're ready to work on 3.8, which is differentials. Okay, so we're in the last section of chapter 3. And this is another section where if we were in regular calculus class, we would spend a long time focusing on this. We're not going to spend as long. We're just going to look at a couple examples that get you a good idea of what we're talking about here. And it's mainly to prepare us for, I think, chapter 5. Yeah, chapter 5. So differentials is what we're looking at here. Okay. So before we get to differentials, we're going to talk about increments. So let's look at increments. So we're going to look at the x and y variable, or a function, basically. So we're going to say, suppose an x variable changes from x sub 1 to x sub 2. This is called the increment in x. Okay, I gotta get rid of this pen. This pen's not cutting it anymore. Okay, let's see about this purple one. Okay, the increment in x. So we're gonna look at how a variable changes. So now the notation that we use for increments looks like this. And this is not meant to be a triangle, it's delta, and delta is the Greek letter D, basically. So this is delta x, and delta stands for a change. So this basically says a change in x. And we find this increment, or this change in x, by taking x sub 1 minus x sub 2. Okay, and we've done this in the past before. So if we want to say find, oh, yep, this pen's not gonna work either. One more purple, and then we got to go to a different color. So let's say it said, find the change in x, or the increment of x, if x goes from 3 to 3.2. Now, I know at first you might be thinking, oh my God, I know how to do subtraction. I know what the difference is there, but just go with me, okay? So we would say that the change in x is going to be 3.2 minus 3, which is 0.2. So what if we want the change in x if x goes from 3 to 2.7. Okay. Now we want to be careful on this one that we notice it's easy to just look at that and do the subtraction and say it's 0.3. But remember that it's the second one minus the first one. So our change in x here will equal 2.7 minus 3, which will give us negative 0.3. So the negative is important when we're looking at increments. Okay. All right, now we can look at increments of y. So increments of y. And so if we look at that, we're going to use the notation change in y. But the thing to think about is y also means our function. So this is going to be f of x plus change in x minus f of x. Okay. Right. So that one doesn't look as nice as this one, but it basically says the same thing. So let's say that we had y is equal to x cubed, and we want the increment from 2 to 2.1. Okay, 2 to 2 point, yeah, I guess it doesn't matter, 2.1. Okay, so what it wants us to do is find what the function is at 2.1, that's this guy, and then subtract what we get when we put in 2. So we're going to find f of 2.1, okay, and that one I will use my calculator for. So 2.1, oops, that is not what I wanted, cubed. Hold on, just hold this for that. Okay, so this gave me 9.261. Okay, and then we find f of 2, which we know is just 8. So if we want the increment in y, or the change in y, we're going to take 9.261 minus 8, and that'll give us 1.261. Okay, so we're finding the change in y. Now, the idea behind this is if you look at the formula for slope, which looks like rise over run, so y2 minus y1. Now again, I know this is going back to the basics. Okay. Okay, using that, couldn't we change the notation to change in y over change in x? And because we've been doing calculus for a couple months now, could we also write this, since we know slope of the tangent line is derivative, could we also write this as dy over dx, or the derivative, dy dx? So essentially what the increments do is they're taking our derivative and they're splitting it into two pieces, the x part and the y part. Okay, so that's what we're looking at here, is splitting this up into two pieces. And it comes right back from our original slope formula. Okay, so those are the increments. So you're looking at the change in the x and the change in the y. Now we're ready for differentials. All right, so let's look at oh, I guess it already says it up there, but we can read differentials. So this says the differential, which is also known as dx, okay, dx from the derivative formula, the differential dx of the independent variable is change in x. Okay? So that's just saying what we noticed over there, tying those together. Now, here's the one that we're really interested in. The differential dy of the dependent variable is dy equals f prime of x dx. Okay. Now, what we're looking at here is that normally we would say that dy dx is the same notation as taking f prime of x. Everybody agree? Those are two different ways of writing the same thing. So now, we've never done this before, but remember what we're talking about here is looking at the top and the bottom separately as increments. So we're going to take the dx part and we're going to multiply it to both sides. So by splitting up the derivative notation, we end up with what we call the differential notation. Okay, so the differential in y and the differential in x. Okay. Now, this can be helpful to us when we are looking at changes in either functions or numbers or profit or lots of different things. When we're looking at incremental changes, we can split that apart and talk about the change in one variable and how it's separate from the change in the other variable. So let me show you a good example of how this is used. And I gotta be honest, I don't know why, but this is one of my favorite problems. Not for any really super useful thing, but it just, I don't know, I like this problem. So the question is, find the square root of 26.5. And then in parentheses over here, I'm going to say no calculator. So not using a calculator here, but we're going to find the square root of 26.5, and we're going to do it using completely with differentials. So what we want to do is we want to figure out what the function is that we're looking at here. So would you agree that we can plug, I mean, I'm asking you for the square root of 26.5, but we could plug other values in there. So could we say that we're looking at the square root function? Is that a function that we're interested in this problem? Okay. Now, the square root of 26.5 is some hideous fraction, decimal, and we don't know what it is, especially without our calculator. But the next thing we want to do is we want to think about a square root that we are familiar with. So how about if we let x equal 25? Okay. So if we let x equal 25 and you were to plug that in here, would we be able to come up with the square root without using a calculator? And we would. The only problem is that's not what we're asking for. We're asking for 26.5 under the square root. So here's where we're going to bring in the differential. Would you agree that the change in x, or the differential or the increment between this number and this number is a positive 1.5, right? So think about it, we take 26.5 minus 25, we get 1.5. So we're not gonna deal with the number 26.5 at all. What we're gonna do is we're gonna split it into two pieces, deal with the 25 and deal with the 1.5. And you're gonna see by splitting it into two easier pieces, this problem is gonna become very nice. Because now we're gonna set up dy. Okay, so we're gonna go dy equals the derivative of this function. So hopefully we've done the derivative of the square root enough times to know we bring down the 1/2 and then there's a square root that goes on the bottom. Okay, so hopefully that derivative is kind of one of those ones that's getting stuck in your mind by now. But then we're immediately going to follow it by dx. So we're going to use this notation, splitting up the derivative notation. So dy, which means the change in y is going to be equal to the derivative times the change in x. Now, we know what we want x to be, and we know what we want dx to be. So we can say that dy equals 1/2 times the square root of 25, and then we can multiply that by 1.5. Okay, right, plugging in. So let's see what happens. So that's gonna be 1, that'll be 5, so 1/10, so 1/10 times 1.5, which will be 0.15. Now, the thing to keep in mind is that this is not the answer to the problem. Is the square root of 26.5 negative, or sorry, not negative, 0.15, okay? No, this is the change in y. So when we do the derivative, sorry, I ran myself out of the room here. So when we do the square root of 25, we get 5. Now we're going to combine that with the change in y, and we'll get that the square root of 26.5 should equal 5.15-ish. Now, okay, remember, we know that it's not exact, but that's a pretty good representation of what the square root of 26.5 is. And if you don't believe it, get your calculator out, go to square root 26.5, boop, and I got 5.1478, blah, 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 but 5.15 is what it rounds to, okay? So the differential, by using something that we're familiar with and then using the change to get to something that's ugly, is very helpful. And guess what? Before there were calculators, how do you think people figured out what the square roots of bigger numbers or weird numbers were? Okay, they used differentials. Okay, so this was I mean, obviously now it's not a big deal because we just stick it in our calculator, but how do you think the calculator got to do it? Okay, someone had to figure out how to do this so that we could then teach the calculator how to do it. Okay, so it does definitely come into play. Okay, so here's another example. Okay, so this says the cost in gas for driving at a particular velocity is given cost equals 125 plus V plus 4,500 over V. Find the change in cost when the velocity changes from 55 to 58 miles per hour. Okay, so as you're driving your car, there's a sweet spot in every car about like what speed you should drive to get the maximum value out of your gas. Okay, most of us drive way faster than that, but anyway, there's a sweet spot for every car. So this function is kind of a function that's kind of giving us that idea of how much it costs when you're driving a particular speed. So this person is going to start at 55 miles per hour, but then they decide they want to go faster. So they're gonna move up to 58 miles per hour. So what we want to see is by moving up to 58 miles per hour, is the cost going up or is the cost going down? Okay, or is it staying the same? Okay, so we're looking for the change in cost, not the change in the whole function, just the change in cost. We already have the change in the velocity. So we know that dv, okay, equals 58 minus 55, which is 3. Okay, and what we're looking for is dc. Now I know the variables are different here, but here what we're looking at is dc equals c prime of v times dv. Okay, so we're going to take the derivative of this function, multiply it by the differential of v, and that should give us the change in just the cost. Okay, now that first means that we need to find our derivative. So let me take a little break over here. So c of x, first thing I'm going to do is just rewrite it. X plus 4,500, or that's not an x, that's a v, sorry. I do know my letters, I promise. Okay, so if we go for the derivative here, that goes away, that leaves us a 1, and then we get minus 4,500 v to the negative 2, so I could put over v squared. Everybody agree? Okay, so we're going to say dc, the change in cost, equals this derivative, 1 minus 4,500 over v squared times the change in velocity. Now, here's the kicker on this one, is that, so remember, when we plug in a velocity into this function, we got to make sure that we plug in the correct number. And the velocity is always the original, okay, the original number. So we're changing from 55, we're starting at v, starting at 55, and then changing 3 miles per hour. So we're using 55 as our velocity. So we'll say dc equals 1 minus 4,500 over 55 squared and then we're going to multiply that by the change in v, which was 3. And let's see what our calculator spits out at us. 1 minus 4,500 divided by 55 squared, boop, and then times 3, boop. So I got negative 1.46. Okay. So the change in cost is, so DC is negative $1.46. Okay. So what that means actually is that in this particular car, 55 miles per hour is not the sweet spot, okay? Because we know if we go to 58 miles per hour, the change in cost is dropping. Now we don't know that 58 is the sweet spot, but we know that in this car, driving 58 miles per hour is gonna save you a little bit of money, but it's gonna save you a little bit of money over driving 55. Okay? Now, that is unless the speed limit is 40 and you're going 58 and then you're gonna get a ticket and it's gonna cost you way more, so you might as well just go the speed limit. But that's not what we're interested in here, right? Okay. Okay, so that's the idea behind the differentials. So yes, there are a couple problems that you're gonna do here, you know, working these out. But mainly I'm wanting you to get used to the fact that what we've done is we've taken the derivative notation, in this case dc dv, but basically dy dx, and we've split it in half. We took the dy and we've split it apart from the dx. And it's the first time we've done that, but we're gonna do it more coming up later. So that's what the idea behind the differentials are. So looking at change in just one variable, not the change of the whole function. Okay? Alrighty, so that's it for differentials. Have fun.